Hi guys, my name is Marcus Lee Jiming from Group 1, and the video today is about community education on multiplexing. These are our group members, and this is a table of content of today's video. Now, what is multiplexing? In telecommunication, multiplexing is the key to efficiency. It's the process of combining multiple data streams into a single complex signal, allowing one communication link to carry more information than ever before. Now, there are 4 techniques of multiplexing method. First one is frequency division multiplexing, FDM, and then time division multiplexing, TDM, wavelength division multiplexing, WDM, and space division multiplexing, SDM. Now, for FDM, have you ever wondered how hundreds of people can talk on their phones or listen to different radio stations at the same time without the signals getting all mixed up? Think of a standard communications line, like a single lane highway. If only one car or one signal can travel at a time, it's incredibly slow and inefficient for everyone else waiting in the line. This is the problem of limited bandwidth. Frequency division multiplexing, or FDM, is our solution. It's like taking the narrow road and expanding it into a massive multi-lane superhighway. Instead of waiting for one signal to finish, FDM allows us to divide the total available space into smaller, non-overlapping frequency lanes. This way, multiple messages can travel simultaneously, side by side, without ever crashing into each other. So, how do we actually move this signal into their own lanes? It happens in 3 main steps. First, we use modulation. Think of your low frequency message, like your voice, as a passenger who needs a lift. We let the passenger hitch a ride on a much faster high frequency carrier wave. In our simulation, we use 3 distinct carriers at 100 Hz, 200 Hz, and 300 Hz to keep things organized. Second, we use guard bands, just like the banded lines or median on a highway. These are small unused gaps of frequency between our lengths that act as a safety buffer to prevent crosstalk, which is that annoying interference you sometimes hear when 2 radio stations bleed into each other. Finally, at the destination, we perform demodulation. We use something called a bandpass filter. You can think of this as a specialized exit ramp that only allows one specific length of frequency through, while blocking all the others, so you hear only the message you intended.
I am Wang Chi-hee, and I will be presenting about time division multiplexing. Firstly, time division multiplexing are communication channels that are divided into time slots. As shown in the diagram, time slots are located between the marks and demarks. The blocks are the time slots. So the characteristics for TDM is that low bitrate signals will be combined together to form high bitrate signals to be transmitted through the high frequency medium. Each message signals will also share the same carrier frequency, but only one message signals will be transmitted within one time slots. Okay. Next, we'll move to the types of TDM. The types of TDM will be evaluated based on 2 aspects: the sampling rate of message signals and the number of bits within each time slots. Sampling rates will bring us synchronous and asynchronous TDM, while number of bits will bring us pulse amplitude modulation and pulse code modulation. So the differences between synchronous TDM and asynchronous TDM is that synchronous TDM will have equal amount of time slots for each message signals, and all of the message signals will have the same sampling rate. But for asynchronous TDM, time slots will only be allocated based on the sampling rates. So message signals with high sampling rates will be allocated with more time slots. Moving to PAM and PCM, which is pulse amplitude modulation and pulse code modulation. For PAM, the message signals will be transmitted digit by digit, which is only a bit by a bit. So for PAM, it will take samples of analog signals and convert it into pulses when transmitting. While for pulse code modulations, it uses word interleaving, which means a group of bits will be transmitted in each time slots. The signals will also be converted into digital signals before transmitting for PCM. Next is the real-life application of TDM. In Malaysia, the telephone systems uses CEPT standards, which relies highly on TDM. For a fast data transmission, hierarchical structures of modified TDM will can.
Now for WDM, you can think of WDM as the optical version of the radio station you listen to in your car. It's a specialized technique used in fiber optic cables that allows us to send multiple streams of data at the exact same time through a single strand of glass. The mechanism is simple. We use lasers to create data signal at different colors or wavelength. These are then bundled together using a device called a multiplexer to travel as one beam of light. Once they reach their destination, a demultiplexer separates them back out so each user gets their specific data. This is a technology that makes our high-speed global internet possible today. Let's break down the 4 steps of now how this actually happens. First generation. We start with our data, which is converted into light signals. Each signal is given its own unique color wavelength, so they stay separate. Next is multiplexing. The mux combines all these different colors into one powerful beam of light. Third is transmission. The combined light travels through the fiber optic cables because each color has its own lane in the spectrum. They travel together without bumping into or interfacing with each other. Finally, demultiplexing. At the receiver, the demux acts as like a filter, splitting the light back into its original color so the individual data streams can be recovered perfectly.
Next, we will move to the SDM. SDM is phase division multiplexing. It is a multiplexing technique where multiple independent signals are transmitted simultaneously using different physical and spatial channels. Unlike TDM, it separates signal by time slot, and for FDM, it separates signal by frequency band. SDM separates signal by space. Example of spectacle channels is different wire in a cable, different core in a multiple core optical fiber, and different antenna in a wireless system. Next is principle of operation. Each signal is assigned an exclusive physical transmission path. Signal can be transmitted at the same time and frequency without server interference. Physical separation simplified receiver design. Small interference may still occur due to the antenna coupling or fiber core crosstalk. At the receiver, each spatial channel is detected independently. Signal processing technique can be used to separate and recover signals. SDM increases system capacity without increasing bandwidth. For the real-world application, first is for optical fiber communication. Each multiple core and few fiber, multiple optical signals sent in parallel in the same fiber. It greatly increases data throughput. Next is for wireless communication. It is implemented using MIO technology and multiple transmit and receive antennas. It's usually used in Wi-Fi, 4G LTE, and 5G systems. For the impact and benefits of multiplexing technique, first, for FDM, it enables simultaneous transmission using different frequency bands, essential for radio, television, and satellite communication. For TDM, it allows multiple users to share the same channel efficiently over time, widely used in digital telephony and data communication. For WDM, it greatly expands optical fiber capacity by using multiple wavelengths, from the backbone of the global internet and cloud service. Lastly, for SDM, it increases system capacity by transmitting multiple signals through separate spatial paths, supporting high-speed networks like 5G and optical fiber systems. Overall impact: this multiplexing technique improves bandwidth efficiency, enables faster and more reliable communication, reduce infrastructure costs, and enhance global connectivity and quality of life. As a conclusion, multiplexing techniques such as SDM, TDM, WDM, and FDM play a vital role in modern communication systems by allowing multiple signals to share the same transmission medium efficiently. They significantly increase data capacity, improve bandwidth utilization, and support high-speed, reliable communication. This technology enables widespread internet access, mobile communication, broadcasting, and global connectivity, thereby contributing to technological advancement, economic growth, and improved quality of life in society. So that's all for our group presentation. Thank you.